Hello, I'm Bryan Fong from HRL Labs, and I'll be speaking on the analysis of randomized benchmarking with realistic noise, or more specifically, the analysis of RB in exchange-only qubits. Measured RB decays in exchange-only qubits look exponential. I'll point you to Matt Reed's talk describing these RB results for exchange-only qubits. But the exchange-only system doesn't satisfy the simplest RB assumptions. The Clifford gates are composite pulses so that different gates have different errors, and the noise in these qubits is 1 over f-like, which is closer to quasi-static than white. Wallman and others have addressed these non-idealities, but we do so here in an explicit exchange-only context. We'll use group Fourier transform theory to analyze RB for composite pulses and quasi-static noise. I won't keep you in suspense. The decays are close to exponential, but that's not the only interesting behavior. The process matrix for RB is given by the average of the product of weighted noisy process matrices with the final inversion process matrix. For regular RB, the weights are all the same for all group elements for all intervals. For interleaved RB, odd weights are uniform, while even weights are all 0, except for the weight of the interleaved group element. These weighting choices are the typical ones, but you can choose whatever weight you want. If you stare at the expression long enough, you'll realize that it's just a convolution over the group. Since it's a convolution, you should do it in Fourier space. In Fourier space, it's just the product of Fourier transforms. Here's the matrix-valued Fourier transform pair. To compute the Fourier transform, add up the Kronecker product of the function and the irreducible representation for each element in the group. Do this for each irrep of the group so that Fourier components are labeled by irreps, which are analogous to wave vectors for scalar Fourier transforms on the real line. Only 2 irreps of Clifford groups usually matter, the trivial irrep and the non-trivial irrep corresponding to the action of Clifford gates on polyproducts. We typically ignore the other irreps because they're exponentially suppressed. In the perfect leakage-free case, each of these 2 Fourier components is a rank 1 projector. Noise introduces perturbations to the projectors, and leakage may increase the rank of the projectors by introducing additional copies of the irreps into the process matrix. Now we noise average the RB process matrix. We can move the noise average under the inverse Fourier transform and do the averaging in the Fourier domain. The key observation here is that for both white and quasi-static noise, the product of Fourier transforms collapses into a power. In the white noise case, the individual averages of each Fourier transform are all the same. In the quasi-static noise case, the Fourier transforms before averaging are all the same because the noise doesn't change within a sequence. We can treat both noise types simultaneously and still take advantage of this simplification of products becoming powers. In the following, we compute noise and sequenced average process matrices, including the effects of white and quasi-static noise, composite pulses, and leakage. Let's turn to the exchange-only qubit. The exchange-only triple dot qubit is formed from 3 spin-1/2 electrons. The top left shows an SEM of a 6-dot device. Just focus on the 3 dots highlighted in red, which trap 3 electrons. The 8-dimensional Hilbert space is described by 3 angular momentum quantum numbers. The encoded state is specified by the total spin S12 of the first 2 dots. The total spin of all 3 dots tells you whether the state is encoded or leaked. And finally, there is a gauge freedom corresponding to the total z-spin m of all 3 dots. Encoded rotations are accomplished by pulsing the exchange gates between the first 2 or the second 2 spins. These give z and n rotations, with z and n axes displaced by 120 degrees. The single qubit Clifford in terms of z and n rotations is given on the right by the table. The exchange-only qubit is subject to exchange errors while doing the z or n rotations, with rotation angles slightly different from the desired ones. Nuclear spins in the dots cause z-directed magnetic fields, which couple the encoded qubit to a leak state. The magnetic noise preserves the m quantum number, so we have a 3-level system with a single leak state. The 3-level system is highlighted in pink in the table of all states. Both exchange and magnetic fluctuations in the model have quasi-static and white noise components. With all these assumptions and the Fourier transform formalism, we can determine the final noise and sequence average process matrix. We show a truncated process matrix here with only components that are necessary for computing basis state preservation and transition. RE in the process matrix comes from the non-trivial irrep. RL and 1 in the process matrix come from the trivial irrep. RE and RL have the same general form, which is shown on the right. The numerator is the usual exponential decay coming from the white noise, and the denominator comes from the quasi-static noise. Both top and bottom depend on spatial noise covariances and the M matrices of numerical coefficients. These M matrices just depend on the Clifford gate pulse sequences and the number of gates in each Clifford. Now we compare the theory and the simulation for the exchange-only qubit. Curves in the plot are theory, and the points are simulation results. The top three curves show the singlet survival probability for quasi-static, white, and combined quasi-static and white noise as a function of number of Cliffords. The bottom three curves are the probability in the leak state for the same three noise types. There is good agreement between theory and simulation for all noise types, and all noise types show qualitatively similar decay or growth. Here's a striking example of how quasi-static noise can break interleaved RB expectations. The plot shows survival probability for X-gate IRB in blue and regular RB in orange. You can see that X-gate IRB survival probability decays more slowly than regular RB. This is because of coherent noise cancellation when the sequence and the noise are not completely random. So for quasi-static noise, blindly subtracting regular and interleaved decay rates can give misleading results. Moving on to 2 qubits or 6 spins, the same error model still preserves the different M blocks. The M equals 1, 0, and -1 blocks are populated now. So we need to analyze RB in 15-dimensional and 20-dimensional spin blocks. There are lots of leak states. One gate set, we can still apply the Fourier transform theory, and we've done so with 2 different 2-qubit gate sets. One gate set is based on the C0 that Steve Wanzura and I found 10 years ago, and another gate set is based on a leakage-controlled CZ gate that Thaddeus Ladd is describing in this meeting. The table on the right shows the pulse sequences for the 2 basic entangling gates and the resulting noised average RB process matrix in the different blocks. Only process matrix components needed for pure basis state preservation and transitions are shown. As an example, the lower right entry in the table shows the M equals 0 blocks process matrix for the LCCZ-based gate set. In this case, there are 2 copies of the non-trivial irrep that are outlined in blue, and 8 copies of the trivial irrep, which is the upper left square, and the red 7x7 block. With noise, the 2 non-trivial irreps couple, and the 7x7 block of trivial irreps also couple. In the 2-qubit case, theory and simulation again agree fairly well, in this case for interleaved memory RB with perfect Clifford gates. The different gate sets have slightly different decay behavior, but the most notable feature is that the leakage-controlled gate set doesn't perfectly mix all the accessible states for long sequences. It does what it was designed to do, which is preventing the spread of leakage. We do expect that including exchange and idle magnetic errors in Clifford gates will result in perfect mixing. So in summary, Fourier transform theory is good for proving theorems and also good for computing decays in real systems, and of course important to our experimental results presented in Matt Reed's talk and other talks in this meeting. White and quasi-static noise RB decays look similar. IRB with quasi-static noise can result in coherent error cancellation. And finally, gate implementations and gate sets affect irrep content and decays of RB. Thank you.